Just a moment. 16B. Question number 16B. For which color of white light is the refractive index? Okay, the least the most. Which color of light travels fastest in any medium other than air?
Why other than air?
Yeah, because they are comparing it with vacuum. And in vacuum and air, there isn't a variation. So probably that's why they're asking you to compare it with air. Or is there some other interpretation issue there?
I don't know. That's my question.
Yeah, the reason why I think they eliminate air is because there is not going to be any change in velocity between vacuum and air. So probably they're just eliminating that as an option. The students, what if they ask that as a question and they don't mention air, and then you just write it doesn't change for air, say for example. So your answer would be technically correct. So they would have to award marks then. Something of that sort, I mean.
So
Sonia, so today I'm just waiting for sufficient participants to join in. She's just asking what are we doing after questions. We will explore further the concept of angle of deviation. So the angle of deviation has some impact. There is something interesting about the angle of deviation and its relationship to the angle of incidence and so on. So we'll just explore that. How many participants? Where can I see that? Isha, do you know where to see that?
there are 30, sir.
30. Okay, we'll just wait a few more minutes.
Yeah. 30 past 5. So can you explain lateral displacement? I didn't get it completely.
Okay.
Wait, can I tell you what I understood till now?
Yeah, sure.
Just a minute. Yeah. So basically, I understood that basically the lateral displacement is the the perpendicular distance between the incident the supposed to be incident ray, like when it's produced forward, and the emergent ray. Is that correct?
Yeah. No, okay, could you just repeat that?
So basically the perpendicular distance between the produced incident ray and emergent ray.
Correct. For a glass slab.
Oh yeah, for a glass slab.
Yeah, because that won't happen in a prism.
Yeah.
Correct.
So,
yeah, Vaishnavi, can you ask your question now?
So the 28th one.
28th one.
I think we did that in the experiment, as an experiment that day, when the lab one, but I couldn't really get it again for why it had two the brighter one.
Yeah, so 28th one, the reason why it happens is because of the phenomenon of multiple reflection. So basically, if you go back to page 77, have you gone to page 77?
Yeah, I read that part, but I still didn't get it.
Which part did you not get?
And I just didn't get why it happened.
So she's asking why is it the brightest?
Why is it?
So just draw the thing that you drew for me. Just continue the drawing that's on the screen right now.
Yeah, I know it. I put it there, but I was wondering if one of you can explain it to her.
Okay.
Can I try?
Who's offering?
Okay, Ishan, go.
Ishan, go.
Fine. So the thing is, okay, the first part of the ray, okay, some of it gets reflected, right? And that's a very small amount. But the second part, that actually like properly bounces off and comes, and that's a major part of it. So most of the ray's brightness is like in that second part. Therefore, that's like so bright, like some 96%.
Hmm. So how many ever rays are there after it's not as bright as the second one, basically?
Yeah, that's
Ah.
because the first ray it just gets reflected on the top only, and that's very small. But the second time it comes, most of it goes to your eye, and that's why it's the brightest.
Hmm.
Sonia, is that fine, or should I explain once?
Explain.
Yeah,
Yeah,
because we
okay.
can't see the diagram very well.
You can't see the diagram very well.
So, like, I mean, like, he's explaining, I don't know which one he's talking about. So, if you could draw it and show us, it would be better.
Yeah, so I think somebody needs to mute their. So just we'll start now. I'll just explain this question and then I'll continue after that. So I request everybody to mute their mics. So I'm just going to answer this question. This is question number, what is it? 16, right? 16? 28. Question 28. Okay, so this is question 28. We are trying to explain why the intensity of the light reduces. Well, one thing is that strictly speaking, I didn't see this in the syllabus document. Multiple reflection of light is not part of the syllabus as far as I am aware. I don't remember seeing any questions also asked from this, but it's an interesting phenomena, so why not have a look at it? The light intensity is something that we actually have not studied, in the sense that we haven't come across this concept. But basically, there is something called intensity of light, which is something that can be measured. It's measured in terms of candelas, if I'm not mistaken. By the way, is the voice and the visuals, everything more or less clear? Does something need to be adjusted, readjusted?
It's fine.
Yeah. All right. So it's measured in candela. So this is something that is useful in terms of measuring the amount of light that is, let us say, coming from a distant galaxy or a star, or otherwise when you're thinking in terms of setting up supermarkets and you're looking at the amount of light that you require to be set up in order to increase your sales. Of course, there is another unit which is used commercially, that is lumens. And this is something, if you go to the supermarket or to a shop, then you can look at the packaging and you will see the intensity of light measured in terms of lumens. It will be written in terms of brightness. They don't talk in terms of intensity, but basically that's what you're looking at. Okay, so if you talk in terms of 100% of the light intensity coming in and falling on the surface, this blue part is the front part of the mirror, and the black line is the reflecting surface. So we were discussing the other day that the light, when it is fall incident on the surface between two media, so there is air here, and this is obviously glass. Then most of the light, that is 96% of the intensity of the light, is going to get refracted and go inside. But there is a 4% which actually gets reflected. You can never avoid reflection from a surface separating the two media. Okay, and there is something called total internal reflection, which we will study a little later, probably 2 classes down the line, where the similar idea will be used. Now what happens is, at the back surface there is going to be a reflection. This is what we studied last year, and that reflection is going to obey your laws of reflection. So incident angle, reflected angle, I've drawn it a bit too small to show all those things. but it will come out from here. So now what will happen is at the boundary between glass and air, the light ray is again going to refract and it's going to go away from the normal. Okay, so it's going to come out like this. All right. Yeah, these two are going to be parallel. So now what happens is that the same thing that happened over here, the 100%, 4% reflected, 96% refracted, right? So over here also in the reverse, when it's going from glass to air, 4% of the remaining intensity of light is going to get reflected inwards. Okay, and 96% of the remaining intensity is going to come out over here. So this is going to be the 96% of the original 96%, right? So and then so on and so forth. Okay, so there's going to be another reflection, another refraction, and so on. So obviously this, if this is 96% of the 96%, then the 4% of 96 went inside. Then while refracting, 96% of that 4% is going to get refracted out again. So each one of these will form a reflection of the same object that gave the light, but the second one is going to be the one which is brightest. So the first one is going to be light, the second one is the brightest. The third one onwards, it will start progressively become dimmer and dimmer. Right? Some people will be able to see the third and the fourth, depends on the your vision capacity. How much light you are able to accommodate and see. People who are naturally older are going to have a reduced capacity in terms of their vision. So yeah, Kian, I had already said that, but from the assignment question, while we were waiting for everybody to join in, there were some doubts and I clarified that. But now we'll move on to the main chapter, which is today we'll be talking about something that I introduced yesterday, which is the angle of deviation. Okay, so the concept of judge marker. Somebody's mic is on, needs to be. Angle of deviation, delta. So what is angle of deviation? Well, when light passes through a prism, then the incident ray gets refracted towards the normal at the first at the junction between the the initial two surfaces, the first refracting surface, and then at the second refracting surface, it's again going to refract. It's going from glass to air, so it's going to bend further. I mean, it's going to bend away from the normal. So we realize that in the case of a prism, unlike the case of a glass slab, the emergent ray is going to be turned away and will not emerge parallel to the path of the incident ray. So therefore, if you produce the incident ray forward and the emergent ray backward, you're going to get an angle of deviation, and that angle of deviation is given the symbol small delta. Okay, so today we are going to study something about the property of this delta. And there's something very interesting that happens with regard to the angle of deviation. And this experiment also I intended to perform. We actually do this experiment. So when you guys come back, we can catch up on the practical aspect of things. Which is that I'll attempt a little later to actually demonstrate that it happens, but I haven't tried it out yet, and I don't know how exactly I'm going to show it to you. So we'll think about that, but let me clear the idea first. So there's a prism and you have a monochromatic light source incident on the surface at some angle of incidence. Okay, now Now, what happens is straightforward. The incident ray will get bent towards the normal, and then on the other side, it's going to get, so these are the normals. It's going to get refracted away from the normal. So this is going to happen. Now, change the angle of incidence for the same light. Okay, so reduce the angle of incidence. So we will do this with various values. You start from like 20 degrees, and then from a 20-degree angle of incidence, you work up all the way to some 60-degree angle of incidence, or 70-degree angle of incidence. Very large angles and very small angles, it becomes a little difficult to draw. But for the same prism setup, uh, draw multiple rays. So this is the first ray, and this is the first emergent ray. Okay, now this is the second incident ray, and naturally, since you have decreased the angle of incidence, the angle of refraction will also decrease, and it's probably going to emerge at another point. So the normal is going to vary at the second surface. I hope that's clear. Okay, now you can keep doing this, and different incident rays will appear. Now there is something interesting that happens when you do this, and you keep increasing the angles from, let's say, something like angle of incidence 20 degrees to something like, I think 70 to 75 degrees should be doable. Every time you do this, you also find out what is the angle of deviation. Okay, so you make a chart. You need the angle of incidence and the angle of deviation. Yeah, Avnish. We do this practically because it's very interesting to actually perform the experiment practically, but it's not part of your practical examination. For the practical examination, you will just have to do a simple one or two angles of incidence going through a prism, and you have to label the angle of incidence, angle of emergence, and the angle of deviation. You don't have to perform this experiment. Okay, so what you will do is you will measure it 20 degrees, and you will write down whatever the angle of deviation is. You will do for 30 degrees, and you will write down the angle of deviation, 40 degrees, 50 degrees, 60 degrees, 70 degrees, and you will note down the different angle of deviations. Remember, okay, I'm not talking about angle of refraction now, I'm talking about angle of deviation. And this produces something very interesting, which is that as you keep increasing the angle of incidence, the angle of deviation will reduce. Okay, Arav, you're supposed to have finished the assignment last week, but since you people are not available over here, I guess you'll have to complete it on your own, and probably bring the assignment back when you come, so that I can have a physical verification. As of now, for the online classes, obviously I'm not going to be able to check the assignment. So we'll just start the classes with some doubts, clarification for about 10-15 minutes, and then we will move on. Is that fine? Okay, so Sonia is saying she can't hear properly. Is that resolved? Sonia, are you able to know what's going on? Are others having any issues with the sound?
Yeah, your voice is cracking a bit.
My voice is cracking a bit. Is it better now? Are you able to hear me better now?
It's okay, you can basically I can hear fine.
You think we are fine?
Even
Yeah.
I can hear fine.
Okay.
Yeah,
Okay.
it's fine. It's probably a connection on your side, on the other person's side.
Sonia, just are you on Wi-Fi or are you using the mobile connection?
Wi-Fi.
Yeah. In fact, even your voice is breaking up. So just check. All right. So to continue, and this is very interesting to actually do it practically.
Can you move the paper a bit higher?
I can't move the paper a bit higher, but somebody's mic. Yeah, Shravan mute. Okay, I can't move the paper higher, but if you tell me what you're not able to see, then I can readjust to that. Because I'm using A3 sheets today, so I have placed the mic at such a height that I can get the whole sheet.
You can continue.
Okay. So, so then what happens when you do this is as you increase the angle of incidence, you will find that the light rays, um, so as you keep increasing the angle of incidence like this, right, you will find that the angle of deviation, which is actually the angle out here, this angle over here. Okay, so that angle is obviously going to decrease as you keep increasing this. Or is it going to increase? Yeah, it's going to decrease. We'll do this practically, but for the time being, you just okay. So it looks like we might run out of the run out of time. So if we do, then we can just come back again. I'll end the meeting and I'll restart it. Then you guys just rejoin again. So what will happen is the angle of deviation will reduce, and then at a certain point of time the angle of deviation will start increasing again. So the emergent ray will sort of go up like this, and then it will come down again. You get the idea of what I'm talking about? Okay, so this can be, then once you have got the the real proof of it is when you graph these two things. If you make a graph of the angle of incidence in the x-axis and the angle of deviation on the y-axis, you get a very interesting graph. So the graph is hey, Vin used up all the papers. Yeah, I'll take that. Sorry, just readjusting. I ran out of A3 sheets. Why does that happen, Darshan? Is well, because of the angle properties. Actually, you will be able to see when you look at the refractive index and how it changes the angles of incidence and angle of emergence. You will see that that has to happen in order to, I mean, I don't know, it's not the reason, but you will see that geometrically you can figure out that that is what is going to happen. So when you make a graph of, oopsie, Kion, Okay, so if you get the angle of incidence, increasing in the x-axis, and on the y-axis, if you put the delta, the angle of deviation, let's say 10, 20, 30, 40, 50, 60, 70. Let's say the angle of deviation, I mean, this is also, I don't know, I can't predict the values, but whatever it is, let's say at 10 degrees, it starts off somewhere there. Then at 20 degrees, it comes here. Then at 30 degrees, it comes there. So the angle of deviation, as you see, is dropping as the angle of incidence increases. Now, at the angle of 40 degrees, you may find that the angle of deviation has increased again. And then at 50 degrees, it's gone up again. 60 degrees, it's gone up. 70 degrees, it's gone up. So now if you look at this graph and you kind of do a freehand curve to connect the graph, then you find something like this. Okay, so what this shows is that as you increase the angle of incidence on one face of a prism, the angle of deviation drops initially and then increases again. Okay, so there are some interesting results as a, I mean, there is something that you can find out for the given prism to you, which is that you can now find out the minimum angle of deviation and the angle of incidence at which the minimum angle of deviation occurs. How would you do that? Well, you have to find the lowest point on the graph, right? Where this and this. So this value over here is your minimum. This is your delta min. And this angle over here, whatever that angle happens to be, is the angle at which the minimum angle of deviation occurs. Will the curve vary for different media? Yeah, the refractive index of the particular, see, we will come to that because in the textbook they have given the value of it. We have now some 4 minutes remaining. So shall I close the meeting and you will rejoin? Is that fine with everybody? But please do it quickly so that we can just finish the last bit.
So, but why do you have to close the meeting?
There is a, because we are using the free version of it, because we haven't yet gone for the enterprise version for it, which we might later. The free version gives us a 40-minute limit per meeting. That's why.
Why is it so? Because it's free.
Rejoin immediately.
Okay. What's the ID?
Same ID.
It's the same ID, right?
Yeah, use the same link. Use the same link.
Okay.
Now, leave meeting.
So I'm just going to finish this meeting. Please rejoin immediately. How do I close this? End meeting.